Hello, welcome back. In this video we are going to focus on the fully connected layer, and we are going to code it only implementing the feedforward function. So as you know, the fully connected layer can be represented as using this form: one layer of neurons, and they are fully connected to every single neuron of the next layer. As I said in the previous video, we can also write this form using a matrix. So we imagine we have a matrix, this matrix with size 3 by 4, and we have an input. So we multiply the matrix by an input that must be 4 by 1, and we will get a 3 by 1 matrix. That will be the output, as we have seen here. Yes, now we have that. But we don't want that because we are not optimizing the function. Once we have made the matrix multiplication, we also add the bias. I haven't said that before, but the bias must be the same size as the output, and we add it, and then we apply a function, an activation function, to the matrix. That would be the feedforward function. So I think that is really easy, but I want now to parallelize our feedforward. How we can do that? We have our weight matrix as here, and instead of multiply by only one input, we will multiply by some concatenated inputs, the number of inputs that you like. In here we have 4 inputs. We will E1, E2, and what will we obtain? We will obtain the output matrix with the same number of columns. So we can nearly optimize our function and compute our dataset using mini batches or batches. I will explain in a few videos how do they work and why they optimize the feedforward function. So I think that's all for now, and we can code it now. The next thing we have to do is that our weight matrix are parameter. They are parameters that need to be optimized. The weight matrix and the bias matrix are parameters that need to be optimized. And how do we do that? Using the backpropagation. In feedforward we go straight forward. In backpropagation we get the error and modify the value, update the value using the error that we have previously obtained, and that and we go back, and that's why we call backpropagation like that. So I think that's all, and we can now write out the code. Yeah, okay. In the fully connected file we can start coding and adding new things. The first thing that I would add is the template, a type name called activation, in which we will define the activation function in each layer. So now I will going to define a type def again, as I've done in other files. We define it dynamic, and we will call that matrix. And we also need to define the vector again, the dynamic, and with the size of 1 vector. Okay, this will I will write this in private, and we can start defining our variables. I will make a lot of variables that explain really well the behavior of our neural network. The first one is the weight matrix, as we have seen before. Now we need a vector called the bias. Okay. Now we can define. Now we will start defining the derivatives of each variable. The derivative of the weight, that's why it's called dW. The derivative of the bias, okay. I haven't said that before, but we usually call set to the result of multiplying the weight matrix by the input and summing it to the bias. That will be set. And 8 will be the result of applying the activation function to set. In the literature that you will read, they are often called with this nomenclature, so you should learn it before. And I am also going to define the derivative of the input in this layer. That would be all. Now we can start defining the class functions. The first thing we should do is defining the constructor. We need to specify the size, the out size, and we also call our we also call our parent class, and that's all. Yep. Now we have to define the init of the fully connected layer. In a previous video we created a lot of virtual functions, and now we need to override the init, the forward, the backpropagation. We are going to define all the functions. Scalar. I'm going to explain what are the different these scalars, these values. Sigma and mu, and the random number generator. Okay. When we are initializing our weight parameters, weight and bias, we are going to use the normal distribution function, and we need to input in this function that we can search on the internet, the normal distribution function, normal distribution in Wikipedia. The the letter mu represents the mean, and sigma represents the standard deviation. So we need to specify the standard deviation and the mean in order to define our function. So we define the weight, we resize our matrix, and we also need to resize our bias. And now we can also resize the derivative of the weights. Resize, okay, this in size, this in outside, okay, and the derivative of the bias. And I have to say that we needed another file that I have included, and I will show you in a few videos, that is called random. In this file I've implemented the normal distribution and others that it is us a lot of work. So I have defined it inside a namespace, so that's why we need to write this. And in this function you need to input the data of the weight. We also need to specify the number of numbers that are inside the weight, the random number generator, the mu, and the sigma function. And we also need to do that for the weights. Yeah, sorry, for bias. That was my mistake. That's all. We have now initialized our function. Now what we need now? The forward function. Our input will be the prep layer data. We now I will define first of all the number of observations or columns of input that we will input. Prep layer data dot calls, number of columns. Okay, so now as we have seen before, mset this and out size. Oops. We need to resize mset because it will change. Will change because we have a different number of columns, so it will be a little bit different. And now we can define our function. You have to you don't have to write no alias, but it prevents some errors that can appear. We multiply the weight by the transpose of the weight matrix, because we have defined our weight matrix using the input size and the output size, and we need now to rotate it. Mset. Now we need to operate using the callwise, and that's all. We have now done the weight multiply, and we have summed the bias. Now what we need now, I will write some comments in order to help you. Set will be W transpose multiply by the input plus the bias. Now what we need now, we need to apply activation function. MA resize this and out size and the number of observations mset and MA. We have not implemented the activation function that we will write all the different kind of activation functions, but inside of here we will our activation function will be applied to this variable and will be saved in MA, in the matrix A. And that's all. We have implemented the feedforward function. Yeah, really good. And now we are going to override other functions like the output, well, that will return MA. Okay, really cool. Okay, we also need to override the back propagation. We are not going to implement it now because we haven't seen the theory, but be sure that we will do it as soon as we look into the theory. So prep layer data, and we also need the next layer data. We'll write a to do, okay? Sorry, we also need to override the back prop data const that will return the matrix where we have applied the derivatives. And we also need to create the update function. We will have optimizers, different kind of optimizers in which we'll modify our weight in different ways. So now I'm going to define a literal string classes you don't need now to understand it, but that's all. Okay, line map vector. It is a map, so don't worry, this is not really important in this class. The most important thing, I think, is the backpropagation. A line map vector w weight dot data weight dot map back bias bias data bias dot size. Okay, that's all. And now we can apply the activation function. The first thing is the derivative of the weight, and the next thing is the weight that we will change inside the function. And we also need to update using the derivative of the bias. This is easy. So that's all for now. We have almost finished the fully connected layer. We only need, as I see, that we need to implement these functions that are not really important, because no, you don't have to use it for now, but we are going to define it. And wait, sorry, not more. Okay, we are going to put this and this, and that's all. We are going to compile it, succeed. I think everything is alright. We don't have errors, no. Okay, so I think that's all. So see you in the next video, that we will be implementing the convolutional or the pooling layer. Thank you for watching it, and let me know in the description if you have any doubts or questions. See you.